Whiteboard. Hello everyone, I hope all of you are doing all right. So I'm just talking about right now pure bending of beams that we already have covered. There is just one more thing that I want to add, but right now let me just complete this example. So you can see that there is two different cases. On the left you have a case A. I'm using the simple bending formula mz over I, and I'm trying to find the pure bending stress. I'm trying to find the bending stress. Maximum bending stress I'm trying to find. So you can see that I'm writing this formula. Now for the case A, you can see that the load is applied to the right. So if this is a cantilever beam, 4000 Newton is applied to the right. It will produce a moment about the y-axis, right? If it is producing the moment about the, if it is producing the moment about the y-axis, then all I have to do is write it. The length of the beam is 10 meter. What is the moment of inertia? So moment of inertia about, I mean the Iyy will be, base is 300 B into the height is 200 BH cube by 12. So this is BH cube by 12. This is 1000 power 3 BH cube by 12. So I'm not sure whether I have space here. BH cube divided by 12. This will give you the stress X max. You can calculate yourself. Now for this one, you already know stress X will come out to be. So for the case B, 3000 Newton is acting upward. If it is acting upward, then there will be a moment about the Z axis, right? So it will be 3000 Newton. But what is the length of the beam? It is 10 meter. What is the Y value? So Y value will be, I think I have made a mistake here. This is Z. So M into Y, I apologize. For maximum, if I'm talking about M by Z over Iy, it cannot be 150, I think. It can be 100, no? M Z over I, and the load is acting to the right. So that means that I will have 100 here. I apologize. A mistake is so easy to be made here. So I will put a 100 here, right? Because if this 4000 Newton is acting like this, then you will have the object, let's say, bend like this. So my neutral axis is this one, let's say, then you have to go 100 millimeter to the right or to the left, whatever. Okay, let's focus our attention back to the second case. So this will be multiplied by, what will be the maximum value of Y? It will be 150 millimeter. Yeah, that's fine. Yes, I appreciate it. Good. And divided by, what is the moment of inertia about the Z axis? Well, that will be, because when now this structure bends, it will bend like this, right? Right. So I'm sure most of you right now are thinking, why are you telling us all of this today? Because we already have covered this, right? I will tell you the reason. So M by over I and Iz is BH cube by 12. What is base? It is 200 and BH cube multiplied by, what is height? 300 divided by 12. So you can see everyone is crystal clear at this point about these concepts, right? Why did I select in Z 100? Why did I select 150 for Y, for maximum stress? So please make sure that when you are writing this, this means max, because the value of Y and Z I have put it. So this slide is slide of revision, I guess, because all of you exactly know. I will wait for, we have a couple of students who are writing. So of course, final exam is right around the corner. I want you to be 100% sure of this. Yes, please.
For the other GT X Max iPhones, minus 10 plus.
That's fine. That's fine. You got a negative value for the second one because I am selecting a positive value of y for the right case, and exactly right. So on the upper surfaces, upper fibers, or the top upper fiber, you have compressive stress. And for the left one, I substituted z equal to I substituted z value of whatever. So you can see for the first case, to the left side, you have fibers who are expanding. In the positive z axis, the fibers are expanding. Should I continue? I will wait for our students. Clear? Okay. Now all of you are saying, why exactly did you cover this, right? The revision. Because of a reason. So let me write a note here. Whatever I am writing here on slide number 2, you can get max from here. So let me write from here on slide number 2, you can get maximum 5 points of multiple choice or objective. Multiple choice, true, false, whatever, fill in the blanks, whatever. I will not give you a full-fledged question, okay? So don't panic because this is going to be something new for you, okay? You can get maximum 5 points, multiple choice, fill in the blank, true, false, objective, whatever. So this is just to make you comfortable, just because exam is right around the corner. I don't want you guys to feel like, oh, come on, why are you teaching us something new? So it will be a motivation for you to concentrate, but at the same time, you can get relaxed that there will be just an objective question, max. Okay, this is what I drew in front of you, right? Now I will take it to the next level. So that's why the topic will become a little more complicated. So now we have the same object one more time. This time around, I will change the question like this and tell me whether you understand it or not. 4,000 Newton like this. And 3,000 Newton like this. Now the problem has really changed. You know why? Because till now in this class, in this semester, every time I have given you any problem, you can look at your notes, all the examples, midterm exam 2, everywhere. I have never given you a case like this. This is the first time you're going through a case like this. Even in your midterm exam 2, there was this problem number 2, which we also did in class. Even that problem was not like this. This is the first time you're going through something like this. That's why I have told you on the top, don't panic. You will only get multiple choice for a complicated problem like this. So how many students agree that actually this is a 5,000 Newton like this, right? Yeah. This part is clear, right? Now what happens is that the whole problem actually now changes. This may seem to you like, oh, it's same, easy. No, it's not easy actually. I will tell you why it's not easy. Now, what is the length of the beam? The length is 10 meter, right? Remember? I told you the cantilever beam is 10 meter and you are looking at the maximum moment that is happening at the support. Everyone knows, right? In a cantilever beam, the maximum moment is supported at the support. Okay. So now tell me, what will be the formula? This is the first time, by the way. So this is the first time, and I will just tell you the formula. Again, don't worry. Well, the formula, the first time we will talk about is stress X is equal to, again, let me draw the axis for you. What is Y? This one, right? As always. Okay. What is Z? Towards the left, as always. Okay, where is X? So I curl my fingers from X to Y. So my X should be along the beam, right? So X is along the beam. It is coming out of the plane of paper. It is coming out of the plane of paper. X is towards me, as always. Z is towards the left, Y is upward. Okay, everything is clear to you, right? So now the formula of X will be minus. Now, can anyone tell me around which axis the moment is acting? 4,000 Newton, the moment is acting about Y axis. 3,000 Newton, the moment is acting about the Z axis. So actually 4,000 and 3,000, you have resolved it. 5,000 was given to me, right? Somebody was putting an inclined load. So you cannot just start using 5,000. Actually, 5,000 would be resolved into the two components. Then you the 5,000 Newton is responsible for two different moments. The 4,000 projection is responsible for turning the beam like this. The 3,000 component is responsible for turning the beam like this. If I just ask you how this 5,000 Newton would bend the beam, your answer will be not only it will bend like this, it will also bend it like this. So there will be a somewhat mixed bending. Do you get my point? So actually the formula is
axial.
exactly very nice. So that's why, excellent. So that's why most of the students will tell me, oh, come on, why don't you write it like this? Minus mz y over iz plus m y z over iy. This is actually the first time we are doing a complicated problem like this. Never ever have you seen a problem like this. That's why I have written on the top, whatever I am writing from here on slide number 2, you can get max 5 points multiple choice from here. So just so that you do not get worried too much. Now you do the number crunching for me. So stress, let's just to be on the safe side, let's call this as A. Let's call this corner B. Let's call this corner D. Let's call this corner C. Why don't you tell me the stress at D? By the way, everyone understands that Z is positive towards the left, right? You do have a good maths, everyone. Z is positive towards the left and Y is positive towards upward. Oh, okay, give me the value of stress D. So it will be minus 10 meter is the length. So mz will be, I don't know, 3,000 multiplied by 10 multiplied by, what is the value of Y? We have to go back. 300 millimeter by 200 millimeter. So let me just make the dimensions. 300 millimeter by 200 millimeter. So you have to bear with me. 300 millimeter by 200 millimeter. Agreed? Okay, now tell me what will be the value of for finding the stress at D. So I have gone to 100 millimeter towards. No, sorry. Why? 150. No? Positive 150. Should it be minus? Yes. I think he's right. Divided by, what is the value of Iz? Iz will be, I don't know, moment of inertia about the Z axis, it will be B into, what is the height? 300 h cube by 12. Agreed? Okay. And then you do a plus. What is the moment about the Y axis? isn't it 4,000 into 10 multiply by, isn't it positive z-axis is 100, correct? How many students agree and how many disagree? Divided by, what is the moment of inertia about the y-axis? It is 300 multiply by BH cube. Why don't all of you double check, because I can make mistake. BH cube by 12. Did I make a mistake? Oh yeah, I did. Correct? Okay. So stress D comes out to be 30 megapascals, correct? It's written in my notes. I'm just copying pasting. So now all of this is new, by the way. Okay. This is the first time you're going through this.
Are you sure it is 30 megapascal?
Yeah, in my notes, again, it's not even my notes, but someone's notes. Why? It's not right.
But I think I found 10 megapascal. I don't know why that's
Achha. Then someone needs to double check, because it's possible that you are right. I'm sorry, I don't know. Can at least one student double check so I can proceed? It's possible that he's right, but it's written in my notes. I have. Then I hope.
Is that minus 150?
This one?
No, the other one.
This is minus 150. Okay, that's fine. Okay, then I think I'm correct then. Okay, so moment of inertia about the z-axis. Okay, good. So now that all of our students understand this, I will proceed. What about the stress at corner B? So I think you can all do it yourself. So stress at corner B is equal to, so do it yourself, but this time you will just substitute, why don't you tell me? The Z value will be negative 100. How many students agree? Correct? Okay, and what about the value of Y? Y will be positive 150, right? Okay. So negative 100 by 1000 and positive 150 by 1000 will be the value of Y. So you will get stress B as negative 30 megapascal. Can you please double check yourself? Thank you. Appreciate it. And then similarly, you can get stress at A. It will be at Y equal to 150 millimeter, correct? Y equal to 150 millimeter. You can double check. At A, I have Y equal to 150 and Z will be 0.1 meter, right? Can anyone double check? Z equal to at A is only 100 millimeter. So your stress A will come out to be 10 megapascals. And similarly, I will write the last thing as, oh, come on. Yes. Stress at point C. No, I need to use an entirely different color. I think light green is nice color. Stress C is equal to, so for point C, I will have Y equal to, what will be the Y value? Anyone, please? 150, right? I think so. Can you double check? Tashin Chan can double check, please. Right? Okay. And then we have Z equal to, no, I generally want everyone to double check. So Z equal to, what is Z value? For C, Z value is 100. Okay. And Z value is negative 100. One of the students has corrected us. Thank you. And Y value is negative 150. So stress C comes out to be negative 10 megapascal. Agree? Okay. So now let's combine the results. We have this fellow is negative 30. This fellow is, by combine the results, I mean compare the results. And this value is 10 megapascals. And this value is, I forgot, 30 megapascals. Sorry? I already used the length. I used the length here. 3000 multiplied by 10, 4000 multiplied by 10. I am applying force. This is a cantilever beam, right? I am applying the load at the end. The maximum moment will happen at the support. So the maximum bending stress will happen at the support. So if the maximum stress happens at the support and you have a cantilever beam, our professors used to tell us that the load is acting at the tip. This multiplied by length will be the supporting moment. I am skipping the statics part for you guys. I think you understand those things. 10 meter is the length of the beam. Everything is fine. Here comes the most important question. I'm not sure whether anyone thought about it till now. Do you remember we used to talk about something called neutral axis, right? What was neutral axis? Anyone? What was the definition of neutral axis?
Zero.
What? Bending stress. The stress is zero. Where is the neutral axis here? That's now that's complicated, right? Because previously I used to ask you where is the maximum stress. You used to tell me that we have to go farthest away from the neutral axis. Easy. So for students who joined on time, they saw that I revised these two problems. When I was trying to find the maximum stress, what did I do? For case A, 100 millimeter, right? For case B, I went, and of course you can forget about double checking the answers if you can. Usman, it's very important that you can see that for Y you substituted 150 here because you went farthest away from the neutral axis. There you substitute Z equal to 100 by 1000, you went farthest away from the neutral axis. Now I am asking you, where is the neutral axis? No. So where is the neutral axis? Is the name of a fiber. What you are saying just at the center, that's a point. There can be infinite lines through that point. My question is, where is the neutral axis? So that fiber, it will be at an angle and we have to find it, because right now if I ask you, where is the maximum stress? Look at all the corners. The maximum stress is where? B and D, right? The maximum stress is not at A and C. A and C only has 10 megapascals. This means that if you have to design the system, you are more concerned about the corner B and D, right? So I will just write the formula and sorry. Because the force is acting at an angle, so neutral axis also has inclined. The formula for now the neutral axis is, that's why I also wrote those lines on the top. Whatever I'm writing from here on slide number 2 onwards, you can get maximum 5 points multiple choice objectives. That's why that's the reason I wrote, because this concept is very new for you guys. So I will write the word neutral axis orientation. It is tan of alpha equal to IZ over IY, MY over mz, and this is what is known as tan of theta. Now you will do the number crunching. I won't do it. Give me the value of alpha. Tan inverse Iz over Iy my over mz. So alpha comes out to be anyone? No? Okay. So tan inverse Iz is 4.5 into 10 power minus 4, I think, meter power 4. Iy I calculated as 2 into 10 power minus 4 meter power 4. My I don't remember. I have to go back. My was 4000 into 10, right? So 4000 into 10, and mz is 3000 into 10 Newton meter. So alpha comes out to be 71.5. Which angle? Oh yeah, okay. Yeah, I know. I have to explain this part. Good question. His question is, how are you even defining this angle? So 6, 5, 4, 3, 2, 1. I have to go back. Now let me answer his question first. Then we will do. This is the angle. You have to go from the positive z-axis. What was the angle? 71.5. So this will be around here 71.5, correct? And this will be 71.5, correct? So let me make sure that I am drawing it correctly. Okay, so this is your neutral axis. And I will draw this like this. 71 point, what was the angle? 71.5. So 70, this is my alpha. Okay, and just to be clear, I will use a nice color, blue color. What is the direction of your moment, by the way? Any student? 90 degree to the force, right? So this is your capital M, right? No? Yes? Okay. And what is this angle? I don't know. Tan theta is equal to perpendicular over base. So theta is perpendicular is my and base is mz. So why don't you do it yourself? Tan theta is equal to perpendicular over base my over mz. Can anyone please tell me that theta? Hanji? So 53. Thank you. 53.1. Okay, now I will ask a question to the whole class, because what is the most important line on this diagram? Anyone? Most important line? Neutral axis, right? What did you say, Mirch? No, it's the neutral axis, because neutral axis we consider as the, again, it's entirely up to how you are thinking, but I think neutral axis is the Most important line, the purple line. Now tell me, where would the maximum bending stress lie? Where would be the maximum bending stress for this problem? We have to go away from the neutral axis. Where? Then, huh? Good. And you know how he figured it out? They figured it out like this. They said we have to go farthest away. So they started going farthest away. Then they started going farthest away. Right? And which are the points that are farthest away? B and D. So actually, this problem should have been done like this. First, you have to calculate the formula for stress. Then you have to calculate the neutral axis. Then you will figure out that B and D are the points of interest. I did not do that. I just calculated all the points A, B, D, C, everything for you. And then I calculated the neutral axis, and we are crystal clear that it's the point B and D that are most important for us. Whatever I am writing from here on slide number 2 onwards, you can get max 5 points multiple choice objectives. So I think it makes complete sense now. Because if I give you a problem like this, it will be hard for you because exam is right around the corner. I don't want to test you guys on a new concept like slide number 2 and 3. But you can get some multiple choice or objectives. So for example, I can ask you, just an example, neutral axis is bent or it is a straight line, for example, in this particular case. Is it inclined, let's say? So you 100% know that for a problem like this, your neutral axis will be inclined. Okay, there are too many lines that I drew. Now I think it makes more sense. Should I proceed? Do we have any question from Hussain, Hasung, or Asan? No? Yes. We have answer from Hasung. No questions. Okay. Okay, and let me write down again. Objective questions from this slide onwards as well. Okay, so let me draw. I will do this topic pretty quickly because again, from the slide number 2 till here, like in total 5 points I'm saying. So I'm not saying 5 points from here and 5 points from the slide 2 and 3. In total, max 5 points I can ask. I don't want to confuse you too much. So this is a revolute or hinge, whatever you want to call it. This is a structure. I have it in the paint as well, I think, but I want to draw it here. Do you want a break right now? Or do you want a break? Okay. Okay. Okay, this is something new. So don't get confused, please. Again, you have a hinge or a revolute, whatever. And we have again a nice support. This area is 0.6 inch square, 0.6 inch square. This area is 1.2 inch square. This is 12 inches and this is 12 inches. This is A, this is C, and this is my B. The question says that you have to determine the value of stress. Determine the value of stress in portions AC and CB. Of the steel bar shown, when the temperature of the bar, you see now, that's why I'm telling you from slide number 2 onwards till the end of it, only 5 points objectives. So just relax and just understand the concepts instead of when the temperature of the bar is, okay, so I'm sorry, it's in British system, but minus 50 degree Fahrenheit. Knowing that a close fit exists, knowing that a close fit exists. You understand close fit, right? Close fit, shrink fit or tight fit, whatever. Knowing that a close fit exists at both of rigid supports, at both of the rigid supports, when the temperature is 75 degree Fahrenheit. What is 75 degree Fahrenheit? It should be around 24 degrees Celsius, no? Double check yourself. So it is 75 degree Fahrenheit. Use the value E equal to 29 into 10 power 6 pound per square inch. And the value of alpha, the coefficient of this expansion, is 6.5 into 10 power 6. So that's why I am going through it quickly. 10 power 6 per degree Fahrenheit for steel. So this is a coefficient that is available to us. So just understand,
What is that?
alpha is the coefficient of expansion. Now, what is the whole point of this problem? The whole point of this problem is someone made this system, designed it, and they designed it when it was at 75 degree Fahrenheit. It is close fit. You understand close fit or shrink fit? It is close fit. It is tightly held, very nice. 75 degree Fahrenheit, they designed it, we are super happy. Now, the problem is that in working condition, the temperatures drop to negative 50 degree Fahrenheit. So you can imagine, right, what will happen? The whole thing will shrink, right? So what will happen at the ends? The ends will be subjected to ridiculous amount of stresses because they want to pull these two ends. So the question says that determine the value of stress in portions AC and CB. You really don't want this structure to break down, right? You really want it to be held properly. So this is why I just wanted to explain to you that this is again an important topic. So we have to determine the reactions at the support, right? So let me just quickly talk about few things. First of all we will do is, let me draw this again one more time. Just bear with me, please. So this is the structure, correct? And we have this again, our, okay, and then we have this fellow is hinged. I think I have already drawn this. Okay, and then quickly, again very quickly, this is what I drew last time. And now I have this fellow. Now this time around, what I will do is I will just remove the support. And what will happen is, this is my structure without any support. Let's say this is A again, this is B, this is C. No, no, I think C was in the middle. So this is C and this is B, if I remember. Now this object, when the temperature dropped, it will shrink, right? We know it. So let me draw this like this. Will shrink to, again, this is my, very quickly, same structure one more time. Please bear with me. And this is, then this one will go like this. Again. Now we are not concerned too much about how much the area will shrink and all that stuff. It will, but it will be not our concern. We are too much worried about, you see how much it has shrunk like this. Okay. Now this is what is known as my delta T. Because of temperatures, it has shrunk, delta T. And similarly, I can also call this as my delta R. I will talk about this later. Now, what I really want to find is how much I need to apply a force that it will come back at its original form. That will be the force or stress that I really want to find. So just bear with me. This is again the same thing one more time. 6, 5, 4, 3, 2, 1. The same structure. And everything is the same. But this time around, I pulled it and I brought it back. So this is my load RB that I really want to find, that we want to apply to this system. This is my RB. That's it. So this strategy will give me the idea what is the value of the stress in portions AC and CB of the steel bar when the temperature of the bar is dropped to negative 50 degree Fahrenheit, because technically this fellow would have shrunk, but at the end of the day, I really want to find this RB that will pull it back to its original form. So that value will be the stress that I really want to find. So just finish the question quickly. The first thing is, what is the change in temperature, anyone? So delta T is negative 50 degree Fahrenheit, your final temperature, minus the 75 degree Fahrenheit 75 degree Fahrenheit, which will give us minus 125 degree Fahrenheit. Okay, now this is a small formula. The change in deflection because of temperature change is alpha multiplied by delta T multiplied by length. Now there are very many students who are saying why the formula is like this, because if a material has greater alpha, then definitely you will have more change in length. If a material already has big length, then there will be subsequently more change in length, right? And delta T, if you have greater change in temperature, the change in the dimension of the object will also be more. So the change in the dimension of the object because of change in temperature is because of its material property alpha. The change in temperature it is subjected to the original length that the object had. So why don't you just do the number crunching for me and finish the question? What is alpha? 6.5 into 10 power minus 6, right? And the units are per degree Fahrenheit. Now I have to multiply this with minus 125 degree Fahrenheit, multiply by the length, the original length, I don't remember. Can anyone tell us? Original length is 12 plus 12, 24. So the delta T change in length because of temperature change comes out to be? No, there is a mistake. Huh? Good. Minus 19.50 into 10 power minus 3 inches. Does it even make sense? Why it's coming out to be negative? Because temperature has dropped, right? So the change in length will be in the negative, right? It will shrink. It will shrink, right? Okay. Then last but not least, why don't you tell me what will be delta R? I think all of the students will tell me it will be, let's call this as 1, this as 2. It will be P1 L1 over A1 E1 plus P2 L2. That's why I made that remark. I don't want to confuse you. So now it is it's very easy, right? So why don't you all focus on this part? This is my single tick, double tick, triple tick. So why don't you focus on the tick, tick and tick part? If this is RB, then what is this one? This is also RB, right? So you keep on cutting. You will only see RB, RB, RB everywhere. So it will be RB into L1. I think we will talk about it. E1 is equal to E2 is 29 into 10 power 6 pound per square inch bracket. What is L1? L1 is 12, I think. So it is 12 inches divided by 0.6. Thank you. 0.6 inch square. And then plus 12 inches divided by 1.2 inch square. Oh, come on. 1.2 inch square. And last but not least, all you have to do is this will be equal to delta R. So I will just write down the answer. My delta R will come out to be, let me use a light green color. Delta R comes out to be 1.0345, 1.0345 into, what is RB? You mean the answer? No, just what is the meaning of RB? I did not understand.
What is the magnitude of RB?
Oh, RB is unknown. RB is unknown. That's what I'm trying to tell you. Look, what is our purpose? Our purpose is that the temperature has dropped. So there will be stresses in this object, right? We have to find how much stresses are induced. If you have to find how much stresses are induced, it is complicated, because in your statics, usually there used to be a force that was applied and you used to find stresses in this class. Happy. The problem is there is no actual real force that you are seeing, but definitely when the temperature has dropped, this thing has shrunk. What you are saying is this has shrunk. Hypothetically, if I remove the right support, it will shrink this much. I will pull it back and I will take it back to its original form. How much load I will apply in pulling it back, that will be my unknown RB. Technically, in a real life problem, you are not removing the support. For sure, it is, come on, it is hinged at both ends. It is attached, if you want to call it, at both ends. So RB is a fictitious quantity that I have introduced right now. I will find it and I will talk about the stress that is induced when the temperature has dropped. I hope I answered your question. Oh, okay. I will tell you where did I take a cut. So this is my object, shrunk it here. I pulled it back. So this is RB. I made a cut here. What is in this portion? RB, right? Because if RB is acting towards the right, RB will be acting towards the left. Okay. Then I made a second cut. What is on this cut? Again RB, because there is one RB that is acting here if the RB is acting here. So for both these sections, I only have RB. That's why for both the cuts, I had RB and I had RB. That's why I pulled out the RB. Did I answer your question? So P1 is equal to RB and P2 is equal to RB. Okay, gentlemen, delta R comes out to be 1.0345 into 10 power minus 6 inch per pound multiplied by RB. Now I understand why were you asking me what is RB. Now that you have this, let's finish the question. But now we have to stop. Can we know how to find RB? Some strategy anyone can tell me? Can we? Is there any way? Any student who can just tell us? Is there any way I can find it? Delta is equal to delta T plus delta R is equal to 0, right? Because if this thing has shrunk and I'm pulling it back, then how much it has shrunk is the same quantity I'm pulling it back. So technically delta R and delta T are equal to each other just in the negative sense. So if this is addition is equal to 0, boom. This plus, do we have delta T? I think we have. So RB comes out to be 18.85 kilopounds, KIPS. Last but not least, we have a lot of students who are asking me, what are the stresses in both the sections? What is the stress in this section? And what is the stress in this section? So stress 1 will be, anyone? Make a cut. What is the force? It is RB divided by area. So it will be P1 over A1, which is equal to 18.85 kilopounds. How many students agree? 18.85 kilopounds divided by the area is 0.6 inch square. It will be 31.42 kilopound per square inch, correct? 31.42 kilopound per square inch. And last but not least, stress 2 will come out to be 18.85 divided by 1.2. It will give me 15.71 kilopound per square inch. This is kilopounds. This is kilopound per square inch. As far as I'm concerned, the semester is over. Just tell me if you have any questions, concerns, reservation. Should I remove the picture? 1 minute. I will. Now. So let me repeat again that from here onwards, slide number 2, whatever I'm writing from here on slide number 2, from here, let's say from slide number 2 onwards, you can get max 5 points all the way up to here. So till here from slide 2. From slide number 2 till here, max 5 points, true, false, multiple choice, fill in the blanks, whatever, maximum or short questions, maximum 5 points, objectives, short questions, whatever. I don't know. I'm still preparing your final exam, but I will just in maximum, if I have to give 5 points maximum, I don't want to make life difficult for anyone. It's also a possibility that I will give only 1 point or probably not at all, but maximum 5 points can come. Yes. So hang on. Look. This is the real problem. Determine the value of stress in portions AC and CBS steel bar shown when the temperature of the bar has become -50. Knowing that initially when you designed the structure, close fit existed at both of the rigid supports and the temperature was 75. But operating condition has become -50. So temperature has dropped. They want you to tell them what are the stresses that are induced in the structure. Yeah.
So delta T.
Is the final minus initial.
No, hocam delta supplement T.
That's the deflection.
Deflection.
The change in length, the deflection due to temperature or thermal deflection, whatever.
Delta reaction, or is the reaction deflection, right?
Yeah. I want to pull it back.
So there is a shrinkage, and also there is a what can I say? There's a pull.
There is a pull that is automatically induced because it is fixed on the right hand, or it is hinged at the right hand. So the fact that there is a hinge at the right, or support for that matter, it doesn't want it to shrink. That's why there are stresses. When I am removing the right support, I am fictitiously removing it, right? Fictitiously. Originally in the real life, the support is there. So there is a stress that is induced, and I'm calling it removing the support and pulling it back, calling it that this is the induced stress.
Hocam ben onu soracağım. We look at the return to.
I showed you, no? Midterm 2.
We have looked, but in first question you said that in return to first question there is no shearing.
No, I sent you a file actually. I sent you a complete file. It had 3 problems. I made that file. I sent it to you on email, on O2 class. It's present. It says some comments on shear stress was the name of the file. You can double click on it. I have written the whole note. So you have to open the O2 class. And alpha is the coefficient of expansion or whatever. Yeah. Yeah. This one?
Yes.
Okay.
They end in the same line.
Yeah, of course. It ends at the same line. This is your original structure. Because of temperature, if I had removed the right support, this object would have shrunk delta T. I would pull it back. So delta R and delta T should be the same, but in the opposite sense. No, you're not. Are you getting my point? Because just imagine if I remove the right support, it shrinks delta. Then I will pull it back. So that will be my delta R, and delta R and delta T are equal to each other just with the negative sign. That's why I said delta T plus delta R is equal to 0. Again, this is all hypothetical discussion of removing the support. Originally, there is a support on the right. It wants to shrink. There will be induced stresses into it. And I have calculated the induced stress, which is stress 1 and stress 2, because of the fact that the temperature has dropped to negative 50 degree Fahrenheit. Okay, let me pause the recording now. You have to see the files on O2 class that I keep sending you. So I think I sent you 8.5, I think so. I don't know, whichever. So questions, you can read this. It has, I think, bending as well as okay. Does this problem has any shear for point A? So forget about the point A being at the even at the surface. Even if the point A was at the center, do we have any shear because of 500-pound force? Actually not, because this load is being applied like this, and your point A, that bar, the force will be longitudinally. So that's why you won't have any shear. No transverse shear, no longitudinal shear. Although you have bending because of this force, because this bar will bend. That's why if you look at here, I doubt that the author has found any shear stress. But now look at the second problem. The load is being applied from the top. If everyone can concentrate, everyone. Yeah, here. Here now the load is being applied from the top. So now because the load is applied from the top, focus on this point here. It will be from the top. So now you have not only transverse shear, you also have longitudinal shear. Here in the previous problem, if you see this load, it was applied on this point, it was applied longitudinally. Although you have bending stress because of this, you don't have any shear. No VQ over IT, even if this point is at the center, doesn't matter. Here you should have. That's why you will see the author has used do we have VQ over IT? Yeah, we have VQ over IT, right? Because now you see that the load is being applied from here. When the load is applied from here, what will happen? There will be a bending stress, and this whole thing, that bar AC, whatever, it will also have longitudinal shear as well, transverse shear and longitudinal shear as well. And the point A, does it lie on the neutral axis? The point A actually also lies at the neutral axis, right? Because my neutral axis is right through the center plane. So point A is actually lying on the neutral axis, and that's why when you talk about shear, I will have a shear for point A. You can zoom in this point A.
In formula, we use the reaction ones, right? Like
V, this V,
yes, sir.
this V, yeah. So for point A, we will have V,
But for example,
800.
deciding the direction of the V must be in the opposite direction, right? So for doing the calculations, we found minus and plus something like that. For example, in the, for example, the bending stress, for the bending stress, we use the reaction moments, right?
But here, for example, if you are putting the load like this, the shearing will be happening like this. So it's VQ over IT. I understand that in my mind that the shearing is happening like this. So the signs, as far as I am concerned, yeah, okay. So it answers your question like this. The author has, if this is 800, the author has put the reaction 800 here. So if you look at here, for the shear, you can see here that it's not the reaction, but the arrows are directed like this. And if you really want to see, like, not only shear is like this, but shearing is also happening longitudinally. So longitudinal shear is by this top arrow and bottom arrow, and the transverse shear is this arrow and this arrow. And please remember that transverse shear value and longitudinal shear value, are they equal to each other? Yes, they are equal to each other. That's why you can see that this arrow and this arrow, their magnitude is the same actually. So you talk about the transverse shear through a particular point, or you talk about a longitudinal shear through a particular point. They are both equal. You can still ask me, but then why V over A that we used to study, that's not the same as VQ over IT? Well, the answer is that V over A is the average shear stress, and VQ over IT gives you the shear stress at a particular layer at a particular point. V over A is the average value. VQ over IT is shear stress at a particular point. That's why the Q, you find Q, right? For a particular layer, you find Q, because VQ over IT gives you shear, transverse or longitudinal at a particular point, at a particular layer. So what I'm trying to tell you is, and again, in this particular problem, you also have TR over IP, you can see. Just do this problem. I have sent you one of these problems in your file, but you can always open the Hibbeler book that is available on Google Drive, I guess, and you can go over these two problems. Again, you can see here the directions. Look at here, nice, beautiful shear. And look at here, this cube. This arrow is directed here, but if you see along this, if you cut it, you will see arrow here and arrow here as well. Thank you so much, everyone. Good luck for your final exam. Have a good day. Bye-bye. If you don't have any questions.